So again, for solutions that are not 100% soluble, I can still write a dissociation equation for those materials. Here is our calcium carbonate equation once again. And as before, we had talked about the original assumption that we kind of go into this unit with is that because it's solid, that there must be zero molarity here, that none of our material must dissolve. But we in fact now know that that is a false assumption, that a very small percentage of it actually does dissolve. So how the heck are we actually going to get these molarities? How do we even measure these amounts? Well, in a lab, it's actually quite simple. We take a beaker, put some of that insoluble material in it. And for the purposes of this example, let's say that this is AgCl, highly insoluble. Well, we would fill up that flask with some water and let it sit, maybe even agitating it a little bit. Slowly but surely, very few, now precious few atoms, precious few ions are actually going to start to slowly dissolve and dissociate into that solution. Now remember, because this has actually been qualified as being insoluble, that means that its molarity is going to be less than 1/10,000th molar. That is ridiculously small. And we would say then that this solution is saturated. Now, saturated simply means that we have the maximum amount of material that can dissolve at that particular period of time under those conditions. Now remember, things like temperature can affect that. If I would increase the temperature, I would make my molecules move a little bit faster, and they'd be able to actually move and migrate into that solution a little bit easier. Generally speaking, as we lower the temperature and the molecules start to move slower, they want to migrate back toward that solid state, so that crystal really wants to remain more intact. In any case, a saturated solution is usually indicated by having the presence of some solid left over after you're trying to make this solution. So now what do we do from here? How do we determine the molarity of this solution? Well, there's two paths that we can actually follow. Both of them lead toward filtration. We would actually take the material and filter it. Now we can decide to capture the solid, which remains in the filter paper up above. Now, as long as I've gone through with good practice and measured the mass of the filter paper before I went and did the filtration, I could allow the material to dry out in the oven and then get the mass afterwards. Now, the mass of the precipitate should actually be lower than what I put into the flask, because remember, some of it actually dissolved. So this lost mass actually represents the amount that has dissolved in that solution. So I can measure the mass of the material that has dissolved. Now, in like manner, I could actually go after the solution instead. So the solution ends up down at the bottom of the flask, and now it actually has some dissolved material on the inside of it. So how would we get that dissolved material back out? Well, you could evaporate that water. And at the end, you should have some solid material present in your dish at the end. That solid that's present represents what had dissolved when you were making that solution. Now you want to be careful here to measure the volume of that solution, so you of course can then calculate what was the molarity. At any rate, we can now actually measure the number of grams that have dissolved per liter of that solution through very quick math. We call this amount a molar solubility. And it's again simply the amount of material that can dissolve per liter. We usually represent these numbers for things that are only slightly soluble. And for this material, you can actually just look this up. It is 0.013 grams per liter. That's what the molar solubility would actually be. Although molar does imply that this number should be in moles. And that's exactly what we're going to do in just a minute. We're actually going to convert that into moles. Now again, remember that this represents the actual quantity that has dissolved. Now when an ionic substance dissolves, it does dissociate to 100%. It's just, again, because it's only slightly soluble, not 100% of the material will actually dissolve. But that does dissolve, that 0.013 grams of it will then 100% dissociate. So again, I don't really like this grams per liter material, although we do often see these numbers reported that way. Let's convert this instead to a molarity. So I'm simply going to swap this out for a molarity, 1.3 times 10 to the negative fourth molar. And yes, that is a very small number. You haven't seen anything yet. The numbers are going to be wicked in this particular unit. But because we know 100% of this molarity actually does in fact go and dissociate, now we're allowed to use stoichiometry. And we can kind of pull this number over to the product side. So again, through multimole ratios, we now know that the molarity of the calcium and the molarity of the carbonate in the solution will also both be 1.3 times 10 to the negative fourth molar.